So 2.5 is going to be doing derivatives with the shortcuts. Okay, and then we're going to talk about the tangent lines. We kind of already talked about the slope of the tangent lines, but now we're actually going to write the equations of the tangent lines, which is really not much harder. And talk about rate of change, which is a fancy way of saying slope. So, the part that I have highlighted here are the basic rule that Hunter just showed us. Okay, so the power rule where you basically take the exponent, you put in front. If there's something there already, you multiply it, and then you just simply subtract 1 to the exponent. Okay, the second rule is that the derivative of any constant is 0. Okay, so if you basically remember those two things, you should be good. The next two rules are just basically you just can derive each term separately. So let's play. So what's the derivative of x to the 4th? 4x cubed. That was a lot faster than doing it the other way. Because if we would have had to use the limit definition, we would have had to FOIL that sucker 4 times. As fun as that sounds, we're not going to do that today. All right, what about number 2? If I have x to the negative 2/3, negative 2/3 x to the negative 5/3, what's the derivative of 3? 0, so it goes away. Everybody good with that? Can I leave it like that? Okay, so technically, yes, you can leave it like this. If you're on the test, on the AP test, and they ask you to find the derivative on the free response part, yes, you can absolutely leave it like that. They ask you to, they say you don't have to simplify. And that's a general rule across the board. But if they ask you to simplify, like for example, if this was a multiple choice question, would they leave an answer like that? No, they're going to have all simplified answers. So I will always reduce stuff, but just be aware on the test, you could technically leave it that way. It is doing what the question asks you to do. Okay, so how do I simplify this if I have a negative exponent? Throw it on the bottom. Good. Well, that wasn't very good. Okay, one thing that they start to get really picky about in this section and kind of from then on is using the correct symbolism. Okay, so if I just throw down an equal sign, I have to kind of be careful about what's on the other side. If I'm just going equal sign, I'm assuming that I'm just going down with the flow. But sometimes, like on question number 3, I'm going to have to rewrite the original function and then take the derivative. Okay, so notation becomes really important. Okay, so question number 3, as it's written, I have a variable that's written in the denominator, and I cannot derive if it's in the denominator, at least not yet. So how would I rewrite that one? So the fraction stays, we have a 1/2, and I'm only going to pull the t out. So the t is going to come out as t to the negative 3. Okay, so I just rewrote the original function. Now I'm going to take the derivative. Notice now I have the notation for h derivative on the top of the, absolutely you could, yes. Okay, so what's the derivative of 5? 0. So then what's the derivative of negative 1/2 t to the negative 3rd? What's negative 1/2 times negative 3? 2. Positive. So what's half? 3 halves, right? So you guys remember fractions, you just multiply the tops together, multiplies the bottoms together. 3 is the same as 3 over 1. Ooh, fractions, okay. And then what's negative 3 minus 1? Negative 4. Okay, so I could leave it like that, but I'm not ever going to. Okay, how would I rewrite this? 3 over 2t to the 4th. Okay, and I technically should say that that is, in fact, the derivative of t. Okay, moving on to question number 4. As written, it is not differentiable, so the first thing I have to do is simplify it and pull my x upstairs. So in its simplified form, what is f of x? So if I have 2 and x both in the quantity, that's cubed, what do I have to do? You don't have to pull both of them up, but what we do have to do is we have to cube both of them. So what's 2 cubed? 8. So I'm going to leave the 8 where it's at. I'm not going to touch it, but I'm going to pull the x up because now I can derive it with basic rule. Okay, so now, what is 5/8 times -3? -15/8. Everybody good with that? I just multiplied 5 times 3 on the top. And then what's -3 minus 1? -4. Okay, so remember on the free response, I can say done. But otherwise, we should really simplify this and say that is -15 over 8x to the 4th. I like that better. Pretty easy? Pretty basic? Okay. They also talk about higher order derivatives. Okay, so just take a look for the most part at the notation of this. Basically what it means, a second derivative is take the derivative of a function and then do it again. Okay, so a second, just keep finding the derivative of the derivative however many times they tell you to. Okay, so just so you guys know, the notation that you will see more often is this with the little hash marks. The, what is that thing? Apostrophe. Okay, you'll see that more often, but every once in a while they'll throw in that other notation with the dy and the dx. Okay, so just be aware of what they're asking you to do. It's just take another derivative. Okay, show example of that. Number 5. Okay, so to do this particular example, I need to start by rewriting my f of x. Okay, what's the rewrite on this? Well, I lost you guys. Where'd you go? Come back. What's my rewrite? 1/2 x. Very good. Okay, so remember the root goes on the denominator, exponent goes on top. Since I'm pulling it upstairs, it's going to turn negative. -2/3. Very nice. Okay, so I'm going to take the first derivative of this. Okay, and what's 1/2 times -2/3? What? Did you ask me a question?
-2/6.
There you go. 2/6 reduces to 1/6. So 2/6 reduces to -1/3. You knew what I meant to say. Okay, and then what's -2/3 minus 1? -5/3. Does everybody see how that's really easy to do? Subtract 1 from the exponent. You just like add the two numbers. You add the numerator and the denominator. So that's really an easy trick. Okay, so the first thing they asked me to find is the first derivative at 1. So I'm going to plug in a 1 on my rewrite, if that's okay with you guys. I'm going to do 1, 3, and then plug in this 1 and put it into the denominator. So what's 1 to the 5/3? 1. So then I have 1 times 3, so there's a 3 on the bottom. So what's the derivative? -1/3. So the slope at 1 would be -1/3. Okay, so then it asked me to find the second derivative at 8. Okay, so I'm going to take this and derive that. Okay, see the one that I'm pointing at? Yep, the 1/3 x to the -5/3.
Can you plug in -8 to the unsimplified version?
Yep, if you prefer to work that way. So what's -1/3 times -5/3? Positive 5/9. Good. Okay, and then if I subtract 1 from -5/3, That's negative, what? 8/3. Gnarly exponents, okay? So then I'm going to plug in negative 8 into this. So I'm going to write 5/9, and then I'm going to plug in negative 8 to the 8/3. Okay, so at this point, this becomes pretty icky. And so on a free response, I would circle it at this point. But if I need to simplify it, I will probably need a calculator. I could do on half of it. Some of it is, this would be one there where you would need a calculator because you need to know what 2 to the 8th power is.
How'd you get 5/9 x?
To get 5/9, see the left hand, see where my arrow is pointing? Okay, so I'm doing negative 1/3 times negative 5/3.
Wow, that's a tiny number.
Hit math fraction.
5/2000.
Are you good, Liz? Okay. Everybody doing good?
We could have done
Yeah. I don't know. It would take a while. All right, so moving down, we have the equation of the tangent line. Go away, little boxy thing. Okay. Since the derivative of a function gives us the slope formula of the tangent line to the graph of the function, the derivative can be used to find equations of the tangent lines. Okay, so I'm going to write this right here as a note. What are the linear forms of equations? Okay, there is y equals mx plus b, and then the one that we're going to use is y minus y1 is equal to m times x minus x1. Okay, this is the easiest one to use, and unless they specifically say the type of form they want it in, we're going to leave it like that. Okay, every once in a while they ask you to find the line that's perpendicular to the tangent line. This is a new term for me. The normal line is simply perpendicular to the tangent line. Okay, so you might star this together just in case they ask you that question. The normal line is perpendicular to the tangent line. Okay, and you guys remember perpendicular is simply the negative reciprocal slope, right? That's old information. All right, so question number 6, let's do this. Find the equation of the tangent line for the function at the point 1, 6. Okay, so first I'm going to find the derivative. So what's the derivative of my function? 6x, perfect. Okay, so then what am I going to use of the point that they gave to me in order to find the slope? I only need one of those numbers to find the slope. Which one do I need? The first one. I only need the x value to find the slope. Okay, so I'm going to say f of 1, which by the way is the slope. I'm going to use the letter m to represent my slope. I'm going to plug that into the x and then simplify that. Okay, so I get 20 minus 6. 20 minus 6 is 14. Okay, so at this point, all I have to do is plug this into my point-slope form and then be done. Okay, so what is my plug-in for point-slope form? Y minus 6 is equal to x minus 1. Done.
So is the f of 1 always your f?
Well, it won't always be 1, but though it's always just the x.
How do you decide whether
It's always the x. Yep, always the x. Okay. Pretty easy. Okay, so they might say write the equation of the tangent line in slope-intercept form. Okay, where you would just take that and set it equal to y. Okay. All right, so moving down, find the equation of the normal line. Okay, so what is the normal line again? Perpendicular slope. So what's the perpendicular slope of 14? Negative 1/14. So now I have the same point that I'm going to use, 1, 6. Write the equation for that. Y minus 6 is equal to negative 1/14 x minus 1. Okay, so a normal line is simply the tangent line to the, not the tangent, the perpendicular to the tangent line. Everybody good there? That's pretty simple, right? Moving on. Okay, so this part right here becomes incredibly important. Okay, and I kind of alluded to this part on that question number 9 of the homework. Okay, so it is important for you to understand that it is not everything is differentiable. Okay, and these are the scenarios where something is not differentiable. Okay, at a hole, at a jump, at a vertical asymptote. Those 3 things are what kind of thing? What are we talking about on those 3 things? We're talking about discontinuity. Okay, so derivatives can only be taken if the function is continuous at that exact spot. Okay, the other 2 are a little bit different. At a sharp turn, very interesting. Okay, so think about at a sharp turn, the tangent line is something that is finding the slope and it only intersects it at one spot. Okay, so kind of at a sharp turn, you could be like, oh, well, this could technically be tangent. This could be tangent. You see what I'm saying? Or like this could be tangent. There's like too many potential tangent equations. And so that's why they cut sharp turns out. Okay, so be very careful about sharp turns. They're going to be rare, but you have to be aware of them. Okay, and then we talked about that on that question number 9. Anytime you get a vertical tangent, which is if you get a slope of undefined, that is not differentiable. Got it? Okay, so let's talk about these ones. Okay, so for these examples, it says find the x values for f of x that is not differentiable, and then give us the reason. Okay, so at where? At 0. So at x equals 0, there is a sharp turn. Okay, so that one, how would you know that? How did you guys know that there is a sharp turn at that exact spot? Okay, so you mentally understand the absolute value has a V shape and has a sharp turn. Okay, so that's why it's important to know what functions look like. That's why we did the sketching part first, so you can visually think about, oh, absolute value, that has a sharp turn in it. Okay, what about question number 9 where you have a piecewise function? Okay, so let's think about this one. First, let's look at each of the pieces. Okay, x squared, is x squared got any discontinuities or sharp turns on it? No, it is totally differentiable. What about just x? Totally continuous, no sharp turns. So what we're worried about is when they come together, is there a sharp turn? Okay, because they do come together at the same spot, right? Okay, so can we graph this and kind of visualize what it would look like? Okay, so on the left, so we're cutting this on the y-axis, we have a parabola with his left arm up, so it's going to look like this. Okay, and then for this one, I have a straight line, right? Okay, so that's kind of a sharp turn. It's not like a super sharp turn, but it's sharp enough, right? It's not like super smooth, like curvy. So the answer is exactly the same as number 8, yeah. What's that? It's still a sharp turn. So like, you would want it to be nice and curvy. So like, for example, I think the best way to explain it is that the left-hand side is curvy, but then all of a sudden it has a quick change in the way you would draw it. So there's a, they would call it a sharp turn. Yes, Abby?
Wouldn't the second part of the piecewise function, wouldn't it just be a vertical line?
The second piece?
Yeah.
No,
Yeah.
just x is like that. So it has a slope of 1, up 1 over 1 with a y-intercept of 0. Okay, what about question number 10? Okay, looking at the two pieces, do we have any issues with the two pieces individually? X squared is good. What about x squared plus 1? Okay, there's nothing wrong with that, but do they come together at the same place? No. Okay, there is a actual jump. It goes from 0 up to 1. So at 0, x equals 0, there is a jump. Okay, so it is not differentiable at 0. Okay, what about question 11? Okay, so this one is a fraction. So the immediate thing I think, oh, we got x is in the denominator. What are the values of x that make this function undefined? 0 and 1. Okay, so now we have to decide what they are. So at 0, what's happening? Okay, so at 0, there's a hole because it would cancel at the top. Okay, and at 1, it's a vertical asymptote. Okay, so two spots on that function where it is not differentiable. Okay, what about question number 12? This is kind of an interesting one. Huh? There is something that happens at 0. There's a vertical. Very nice. Okay, I'll show you. There's a vertical tangent. Okay, so if you were going to graph this, an x cubed is basically a John Travolta that is turned on its side. Okay, so you're looking where, right at that origin spot, how it turns right there. Right there, there happens to be a vertical asymptote. Or vertical, not vertical asymptote, excuse me, vertical tangent. Vertical tangent, so like, where the slope of the line at that spot is straight up and down. So it's hard to see. You just have to look for a really, so like, I think the easiest way to tell is like, if you think about doing the vertical line test, the place where it kind of, you're like, that looks kind of close, is usually a place where it would have a vertical asymptote. Or vertical, gosh, I keep saying the wrong word. Vertical tangent. All right, here's the last piece, and this is pretty simple. Rates of change. Okay, you guys know average rate of change already, don't you? You have learned this before, you probably just maybe forgot it. Okay, it is simply the slope, it is the change in y or the change in x. On a function, okay, usually you'll find average rate of change on a straight line. That's what you've really practiced a lot of in the past. But now if you do it on, let's say, a cubic, for question number 13, you have to figure out what the y values are and then do the slope formula. Okay, so let's do that one real quick. So on question number 13, they give us two x values, but we do not know what the y values are, so we need the function to figure that out. So we're not gonna derive it yet. No, actually no deriving at all on this. That's actually for instantaneous rate of change. So all we're going to do for average rate of change is we're going to plug in the x values into the existing function and come out with the corresponding y value. So this would be 1,000 minus 20, or plus, excuse me, 20. So 1,020. Whoa. Okay, and then I'm going to do the same thing with the other x value, which is 30. So 30 cubed plus 2 times 30. So what is that, 9? No, 27, geez. What am I thinking? 1, 2, 3 plus 60. Wow, they use some pretty nice numbers. Okay, so do you see the ordered pairs that I'm getting out of this? So I have 10 and 10, 20. That's going to be my x1, my y1. And the second point that I found is 30 and 27,060. So that's my x2, y2. See where I'm doing that? Okay, so then I just use the slope formula for that. So it's y2 minus y1. So m is going to equal 27,060 minus 1,020 over 30 minus 20. 10. Sorry, I did some adding in my head. 10, thank you.
26,000.
1,040 over 20, and I bet that simplifies. 1302, which is a very steep slope.
So it's not for every y it goes up to that mark.
So basically, so imagine that you have this like, ooh, this is hard to, because it's so steep. So you got this John Travolta, right? And here's 10, and here's 30, and here's that first point, and then here's that other point. The slope is the average rate. So if you draw a straight line, what's the average slope between those 2 points?
So for every one.
Yes, well, every 1302 up, 1 over. So it's it's going up a lot more than over. So that's kind of a silly thing to find, because it's just finding an average. The instantaneous rate of change is much more valuable. Okay, so instantaneous rate of change is just simply finding the derivative and then plugging in the x value. Okay, so what's the derivative of my given function? 3x squared plus 2, and then all I do at that point is find my derivative at 10. Instantaneous is exactly the slope at that spot. So instantaneous is the slope at that spot. And you use the derivative for that one, exactly. Not for average. So what is this, 300 plus 2, so 302. Anybody else get that? Okay, so that would be like on my little graph right here. At 10, this tangent line is kind of like that. It's obviously not drawn to scale at all, but you kind of get the gist of it. All right, I think that's it, isn't it? You done? Okay. So let's do. Oh, I already started doing this. It's actually not too bad. Let's see. Let's just cut this in half and let's do 1 through 31 for Monday. 1 through 31. What's that?
Like 7 through 10 says find the value of